Uh, I'm Mykyta Bobylyow, PhD student from Bogomoletz Institute of Physiology. Uh, I will tell about hypocalcin, neuronal calcium sensor uh, uh, that can have mutation which leads to focal dystonia from one substitution, one amino acid substitution. On the left side of slide, contour map of mountain from Patagonia, from Argentina, called Sierra Torre. Very nice mountain. Okay, let's go to next slide. Hypocalcin mhm, is a neuronal calcium sensor. It has four EF-hence domains. One is dysfunctional and can't bind calcium. And in experimental practice, possibility to bind three calcium ions supposed to be quite low. Typically, no, in experimental practice, suppose that this protein binds either one or two calcium sensors in wild nature in cell. This is a structure from X-ray crystallized structure, so it may be incorrect in some ways. By binding three calcium sensors, two calcium two calcium ions, this protein activate myristoyl switch by releasing an terminal from hydrophobic. Hydrophobic pocket of this protein, and terminal of this protein modified in that way by myristoyl that it can bind to membrane. So it's a peripheral protein which not submerged in membrane, but has only one contact point on N terminal. This work lit up from hypothesis that this protein preferably binds to membrane enriched by PIP2 lipid, one of phosphoinositols that primarily distributed on inner leaflet of plasmatic membrane. Еще. Okay. On left side of slide, we can see pyramidal hippocampal neuron. Green is hypocalcin, and magenta purple color is PSD95 protein. Is from our project in this project in team. Everyone except me does fluorescent microscopy. Okay, so other hypothesis is that this protein sorted by membrane curvature, by its folds. Other hypothesis is that it's primarily binds to ordered membrane regions. So we was testing hypothesis about binding PIP2 and actually about preferable binding to lipid rafts, but I guess all atom molecular dynamics in this case isn't best choice. So yeah, uh, what's oh, yeah. So approach was a lot on molecular dynamics, finding that orientation of mutated form of hypocalcin is significantly different from normal protein, from wild type protein, and it leads to discrepancy of behavior, uh, different overall difference of behavior, membrane bound state behavior of mutant form. I'm sorry. So aim was a comparison of wild type and 75 K form. I must say that this substitution, amino acid substitution, and 75K is located on second EF hand. Can I show it on? Yeah, it. Uh, yeah, this one. So it's substitution of. Uh, 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 On this EFM domain, this is second EFM domain, this is third, this is fourth. And it's substitution from polarized histidine N to positively charged lysine K. Okay, so let's go to from aim and objectives to observables, to methodology. So we've done for this presentation, overall we've done 5 simulation with other type of membrane and without protein, and all done with in charm 36 polarized all atom force field, optimized for a lipid simulation with lipids in simulation box with membranes, etc. But in this presentation, in this case, we will look at data from 2 simulations. So observables in this case is three angles. Significant angles in this case is phi and theta, where phi is psi and theta, where psi is rotation along own axis of protein. Axis is principal longest principal axis of protein. We've chose to we've chose longest and yeah, and tilt angle is tilt of this axis to membrane normal vector. But actually, I was supposing that membrane normal is 0, 1 vector perpendicular to z to box, to walls of box. I'm sorry for strange note. Yeah, and let's go two observables and tell more about them. So precision, it has no meaning to look at precision in this case. These angles, no, rotation calculated in ZYZ, Euler angles последовательность. I don't remember how it's named in English. Precision has no meaning because membrane yeah, I'm sorry. Ну, да, ну, я хотел сказать, что мембрана униформная, и у нас periodic boundary conditions, у нас periodic boundary conditions накладені, тому, скоріш за все, процесія не буде відповідати ну, тому, що відбувається в дикій природі, і дивитись на неї, скоріш за все, не варто. Так, about energy contributions, I've tried to do some decomposition on electrostatic and non-polar hydrophobic. I don't know why it's called hydrophobic on slide. Non-polar interactions of this protein, and yeah, and non-polar interactions represented by solvent accessible surface area. It's specific metric because it's not unit of measurement here is not kilocalorie divided by mole, but nanometer squared. Yet it's best proxy for non-polar interactions, I guess. And yeah, by Boltzmann inversions of two variables like tilt and spin angles, or by some comparison to the electrostatic energy, we can get some landscapes that will tell us where is minima of this protein membrane bound state, and yeah, system. Overall equilibration was done in 3 stages. I guess it will take too much time to tell about equilibration protocol. So yeah, system was equilibrated in 3 stages of NVT equilibration, and then in 3 stages of NPT equilibration, and simulation was done in NPT ensembler with Parinella-Reumann and thermostat, Parinella-Reumann thermostat and Noes-Hoover barostat, because and we've selected starting from 100 nanoseconds part of trajectory, because for N75K there is unbinding of myristoyl in this window from 50 to 100 nanoseconds, and it doesn't lead to overall unbinding of protein, but this rare event shouldn't be in analysis. Yeah, in secondary structure analysis, main difference in first EF hand. EF hands of neuronal calcium sensors, they are bound one to one. So EF hand 1 to EF hand 2 and EF hand 3 to EF hand 4 by antiparallel beta sheets. And I guess this binding doesn't happen in mutant form. So we have a large significant difference for DSSP in region of first EF hand. And in second, a less significant, less pronounced dynamic cross-coloration matrix shows that near first EF hand, negative correlations are elevated for mutant form. And about orientation, so potential of mean force maps for wild type and then 75K forms show, first of all, that normal form has some equilibrated state, which is hard to escape in times of this simulation. And mutant form is overall unstable, and minimized state near to membrane normal vector. So it's mostly perpendicular to membrane. Yeah, definitely. Let's skip these two slides. So I guess I don't think that can continue. I know that I take too much time. I guess I will stop here because I'm.
Yes, yeah.
Okay, thank you for your attention.
Since we know now about the behavior of this protein, so how we far away from good treatment of dystonia?
About treatment of dystonia, I hope that this work will develop to testing if myristylated polypeptides that bind to inner leaf of membrane can stabilize orientation of mutant form. Maybe orientation is key is key difference between wild type and mutant form, in meaning that if protein not bound to membrane and membrane binding of HPCA, wild type HPCA, happens in that way that EF hands are oriented to cytosol. So protein can bind this surface with high probability. If protein is perpendicular and spinning, it's almost impossible to bind this surface for other protein. We will check protein-protein interaction with adapter protein too, because HPCA acts as secondary messenger in AMPA receptor endocytosis, long-term depression-induced AMPA endocytosis on dendrite spines, on postsynapse, on neuronal postsynapse. Too much information, I guess. Yeah. Okay. Yeah. So I hope that this will lead to some treatment, treatment for dystonia.
Thank you. No. Thank you.
Okay.
Ми маємо завершити на сесію.